Okay, today I'm really excited about the topic we will discuss. We will talk about neuroscience and computer architecture in general designing system. And we have two prominent guests who will discuss this topic. We have Tim Sherwood, who is a professor at UCSB, and he has done some amazing works in computer architecture and systems. Most probably there is no student working in computer architecture who did not use scene points. But today we will not talk about any of those works because we will be focusing on an area which is very new. Tim is one of the few people who started designing hardware using neuro-inspired computation. On the other hand, our second guest is Abhishek Bhattacharjee, who is a professor at Yale University. And similar to Tim, he has a wide interest in working at the boundary of computer systems and architecture, especially a lot of work on memory systems. But today we will learn about some really exciting and cool things that are going on in neuroscience and computer architecture. And he is one of the pioneers in designing brain-computer interface using software and hardware techniques. So thank you very much for your time. Welcome.
Thank you for having us.
Thanks, Amita. Thanks for organizing this.
So first, I think I'm really interested to know that how did you start in working this new topic? Because you started with traditional computer architecture and systems, and then you transitioned to this very new topic. And I would like to know what's the personal story there is behind it and what motivated you to start working on this area.
Sure. Who wants to go first?
Go ahead, Tim.
Yeah, so, I mean, I've always been really interested in, computer architecture to me is a very broad field. And so how it connects to all these other fields is something that I've always been interested in. I mean, to me, the computer architecture is unique amongst the sort of computing fields in the sense that we deal with the physical act of computing, right? Where, what it means to actually move electrons around or whatever it takes in order to actually do the computation. But yet we have this really broader view of how, what it means to be a computation and how to support computation in some general way. And so that to me has always just been sort of one of the things that connected to me. I actually entered into this, even though I've been doing some more neuro-inspired architecture stuff, as of late, I want to be very clear that there's a long history of sort of neuromorphic architectures and neuromorphic, brain-inspired computing that goes back many, many decades that sort of I'm a late entrant into. But, the story for me is one where, I was doing this work with Dmitry Strukov and Medhaven at UCSB, and on, at the time, what was called race logic, which was sort of like how you do computation with time. The idea being how long it takes for something to happen can be a way to encode a value, and then you can actually sort of modify these temporal encoded data, and how these temporal encoded data sort of produce new temporally encoded data, and how do you do some computation that way. And for me, we had this, Dmitry, I really credit him with coming up with those core operators. We figured out that there was these notions of min and max and some delay operations, and we were like, oh, this is really cool. We can do all kinds of neat stuff with this, and look, we can do some like dynamic programming things. And we kind of had worked out all this hardware implementation stuff. And then but we were really struggling with making it sort of general purpose, like what could we do and what couldn't we do with it. And in parallel to that, Jim Smith, in his using his emeritus status, has really just, really tried to understand what it means to, what is the sort of mechanistic model of computation, if I will, for that's going on in the brain. That's something he's really interested in. And then we got connected up, and we're like, oh my gosh, you're doing operators X, Y, and Z, and we're doing operators, Y, Z, and W. And we realized that actually we're all doing the same thing. And, we had never come up with any sort of general purpose stuff that he had come up with. And he had never thought about anything being implementable in hardware in some way. And so there's this like really intense period of like trying to find this connection. And so, I've been really pretty deeply involved since then on. So for me, it was very sort of happy accidents all along. My whole career is a series of happy accidents, I think. This is just another example of that. That's pretty much it.
Yeah, that sounds pretty interesting. Abhishek, what's your story?
Yeah, actually, there's a lot of, I think, similarity with what Tim described, like a sequence of happy accidents and just really happenstance. I mean, I guess at a core level, I've always been really interested for personal reasons in technologies that can help offer ways of mitigating mental illnesses and mental health issues. So, like many other families, my family has had, issues in sort of that dealing with mental health problems. And so that's something that's always been, I guess, an area that's been very like personal to me. And I've wanted to work in that space. In fact, before going to graduate school, I was seriously contemplating going into medicine, versus grad school in ECS. So I think one of the first people that got me thinking more seriously about linking what I was doing in computer science with the brain sciences was Doug Clark, who's now an emeritus professor at Princeton. And I took a class that he and my advisor, Margaret Martinosi, offered called Great Moments in Computing. It was an awesome class. I think, in fact, if you're curious, I'm sure the readings are somewhere online. One of the interesting discussions that came out of that for me was we studied virtual memory, and I had this really interesting chat with Doug about how he thought about virtual memory as being a naturally occurring phenomenon. So one of the examples that he raised was the visual cortex is able to sort of keep track of a finite number of objects before our ability to recall specifics about those objects starts to degrade. So there's like an element of something like a replacement policy essentially in our visual cortex that seems to govern our ability to make detailed sense of whatever visual stimuli we're getting. So I thought that was very interesting. And actually, in a funny way, I would say that conversation is what sort of prompted me to get into my virtual memory research in a way. It's just something that made me read more about virtual memory, and kind of I went into the whole TLB line of work from that. But it was always, I think, at the back of my mind. And I mean, what really happened for me is that I would keep reading about these brain interface technologies and, the strides being made in mechanisms to probe the brain, understand low-level details about brain architecture. There were so many similarities with computer architecture that I saw that were interesting. The role of abstractions is so critical to that field. There's a notion of neurons, which seems to mimic what goes on perhaps at the transistor level. There's neural circuits that to me, look a lot like microarchitecture. Then there's complex handshaking protocols between different brain subcenters that remind me of the kinds of things we study in architecture and so on. And so there were similarities there that would keep appealing to me. Other similarities that would appeal to me are, for example, the role of tools and methodologies and simulators in the process of scientific inquiry. And in neuroscience, the interesting thing is, they have similar challenges to what we face. So if you want to study low level neural activity, which is the equivalent of perhaps our circuit level place and route RTL kind of work, they do experiments on primitive organisms, so that essentially they have the equivalent of like bounded simulation times. And then when they want to start getting closer and closer to like human behavior and studying that, they have more and more abstract representations of how our cognitive functions work. So those kinds of, I think, links, some of them aren't even very, I think, direct links, a little bit more, I would say, tenuous, but they've always sort of had me hooked into the space. And yeah, and I mean, more kind of practically, I think what happened is in 2016, I think right after I got tenure, I spent a summer at this boot camp for neuroscience at Princeton. So I went back to the Princeton Neuroscience Institute, and they basically trained people over the summer on doing animal work and getting in the lab. And so I learned how to do craniotomies on houseflies, zebrafish, and like, aggressively bigger animals. And it was, I didn't go in with some kind of set agenda for how I would link my work to it, but the links were always there, whether it was in the tools that were being used, the interfacing technologies, the discussion of information representation, the abstractions. There were just so many links. So that's what really led to it. And then, I've been lucky to find good collaborators. I think I found a bunch of people at Princeton Neuroscience Institute who were very sort of computationally minded and sympathetic to the kinds of problems we look at. And yeah, it sort of went from there.
That sounds very interesting. So for both of you, it seems like there was always an interest, but at the same time, there was a spark of idea that came through some collaboration and some other activities. So it really amazes me that you said that there is already a lot of similarity between how we design our computers and how the neuroscientists look at the brain. But if you think about it, the architects, they are only focused on designing computers, and the neuroscientists, they are trying to learn how the brain works. And it recurs this unique insight that suddenly you see the similarity and you say that, oh, they look very same, and we can actually combine and merge and do something greater. So it may seem to you that this was the intuition came easily, but I would say that that's a really important thing. And now that you have the insight, you can motivate other people and you can take it way farther. But the starting position, I would say that's really important, and it requires certain type of expertise. So I'm really grateful that you chose this path.
Well, one interesting thing to me that I think really drove a lot of my interest was this. To me, the brain sciences seems like a field where the abstractions are being figured out still. I mean, there's a lot of work at kind of the low level neural circuit level. There's a lot of work at the cognitive and psychological level, but the links between those two abstractions, that's still very much, that's the active area of research which people are trying to make progress on. And I guess what was really interesting to me is, as computer architects, we know the fundamental building blocks of the systems that we build. So we've been able to layer our abstractions. We can make decisions about where the hardware software contract is, where is the contract between different layers. But in the brain sciences, it's sort of in reverse. They're trying to reverse engineer how the brain works. And so it's, neuroscientists they just can't go in and kind of come up with their own abstractions. And that was interesting to me, the idea that you might have to figure out what the abstractions are and work from there. And I'm pretty sure, this is, I think, one of the things I really like. One of the many things I really like about the race logic work is like, I feel like, and, I want to hear Tim's perspective on this, but something that really excited me was that it didn't, there were more fundamental principles about computation in nature that were lifted out of the substrate, the underlying substrate of the brain, and were kind of generalized into something that could be workable, say in CMOS or in more conventional digital logic. That's something I found really exciting. So Tim, I wanted to sort of hear your thoughts on that and other opportunities for that kind of thing.
Tim, I think you're muted.
I did, sorry. Yeah, I was saying that your point about abstractions is right on the nose. I mean, I think that, and that's one of the things that's, computer science, you could argue, is the science of abstractions, right? I mean, like, it's a really critical part of what it means to do computing. And you're absolutely right. It's like, what are the abstractions that make sense there? And I feel like the neuroscience of the field has a lot of knowledge now about, individual neurons and, and the hundreds of different types there are, and all, the ways that they behave sort of by themselves or in units of two. And then there's really interesting cognitive models at a very high level, but there's this like really squishy middle where people are trying to like, build down from the top and up from the bottom, and it's still really unclear as to how they connect and where they connect and what are the abstractions that define, their operation in some meaningful way. And so, I think there's a lot of opportunity there. I think one of the things that, one of the things that, is that abstraction, it's easy to get caught up talking about sort of like an individual neuron, and let's build a model of that individual neuron. And, like I said, there's so many different types and they do all kinds of different things. But to me, the analog to that is sort of in the digital space would be like looking at a transistor and what's a model of a transistor. And you could have a really beautiful model of a transistor and all of its different dynamics, but like where it gets used, some of them are used to do, in a analog fashion, some of them are, but and you can do all kinds of really clever tricks with them, but at the same time, if you want to understand the computation that happens in a computer, there's a regime of operation which you can simplify down to this very simple form. It's like they get put together into logic gates, and they have these properties as collections. And to me, I don't know whether that exists or not in nature. I think that's a fundamental question that's sort of remaining. But it's a really rich area to kind of explore the abstractions. And so that's when race logic was like, okay, this is a simple abstraction. We can have some very simple rules that govern its operation. Then the question becomes theoretical. What can you do with it? What can't you do with it? What problems are hard and what problems are easy? And then you can, from there, kind of ask questions back like, well, are those problems really hard, or are those problems really easy in different ways? So yeah, I think that sort of notion of like building hypotheses where those hypotheses are models and then seeing what those models are capable of, I think is kind of an interesting, rich area. And I think it's something actually that I think that philosophy, whether it's neuro-inspired or not, is something that's an interesting thing for us to think about as a computer architect. If I look at, for example, programming languages as a field, they kind of take this. Some researchers in that space take this notion of like, what happens if everything in my language is a channel, and what do channels send? They send other channels, and just channels all the way down, and like what works and what doesn't, and how does it break? I think that's really interesting fundamental work, and I think there's opportunity to do that kind of work in computer architecture as well. And I think that's one of the reasons some of this type of work connects with me. I'm not sure if I answered your question though, Abhishek.
No, you did. You did. It actually brings. No. That was actually kind of what I was getting at, and it, just to riff off that, actually, I think one of the things that made me really set up with the race logic work in particular was that. So I mean, it's obviously you've shown how to use some of these principles of brain-like computing to potentially offer a path towards building systems that are extremely energy efficient, power efficient. I mean, you can clearly see you can see a path where that's going to be helpful for computer architects. But the other piece that I think is really cool is how influential I think it could even be in the design of systems to help the brain sciences. So for example, one of the things with race logic that got me excited was it seems like it's potentially a more natural mode of information encoding that could permit you to interface more naturally with the brain. So if I'm building a brain computer interface and I'm power constrained, and just maybe taking a step back, with a lot of the brain computer interface technologies that we build, the big problem is really power, because if you want the state of the art in terms of BCIs today is devices that you can implant in, around, or on the brain tissue. So even temperature increases of about 1 degree Celsius, they can prompt for, if they're in the patients in whom they're implanted, they can prompt mania, they can prompt hallucinations. So power is a real concern. And the big problem in that field is, how can you have a high bandwidth link to the brain? How do you lift as much data as you can from the brain, process it fast, find signatures of things like maybe a seizure, or maybe there's unintentional movement because the patient suffers from Parkinson's disease or some variation? How do you do this fast? And how do you stimulate the brain in sub-millisecond scale to actually mitigate the symptoms of some of these disorders? The big problem is, how do you do it in an acceptable power budget that doesn't overheat the brain tissue? One of the big problems right now in the neuroscience field is that there's this like major tension between how do we record as much data as possible at the sampling rates that we think are useful while staying under that power budget. And there's no consensus on this. Some people in the field think that we should downsample our signals and risk the idea of losing important information. Other people say you can't lose important information, just probe fewer areas in the brain. If you look at the power distribution of one of these devices, the central problem really is the information encoding. It's basically all of the analog to digital conversion that you have to do when you interface with the brain signals, then the digital processing, and then back to the analog signals to do the stimulation. When I read the race logic paper, one of the things I found really interesting was maybe you can find ways to bypass some of that if you have a more natural way of fitting in with the neural signals.
Yeah, if I can just actually, I want to ask a question, because that's a very interesting way of framing the problem there. I mean, and actually, I'm sort of connecting this mind to a very similar problem in high energy physics. So when you have, they have a somewhat similar problem. These huge detectors, right? And they just have tons of sensors, and they're just getting bombarded with these high energy particles. And somewhere hidden deep in there is the information that they need in order to be able to, tease apart the fundamental properties of these particles. So they're constantly dealing with this sort of downsampling problem, and they have a bunch of techniques, for sort of like, how do I do this in a way that is not biasing all of my, because the method of sampling, the method of computation, and the scientific question that you're trying to answer now become tangled in a way, right? Because changing one will change the data that you see, which will change your ability to answer the question you're trying to answer, but you don't know what to build because you're trying to answer this question. And it seems like kind of a similar set of problems is existing here, where I'm not sure if you've looked at anything that they've done there.
Actually, yeah, that's something that is of big interest actually in the community. There's, in this entire debate of like how aggressively can we downsample, and what is useless neural data, what can we throw away for decoding. Some of the examples that are frequently brought up in the community are things like space exploration, getting images from satellites. I mean, a lot of the sort of downsampling techniques for high energy physics, space exploration, this is the kind of stuff that frequently crops up. I think one of the challenges in this space is that we know so little about the brain that it's difficult to know what is useful and what isn't. And particularly when you have closed loop systems which are acting on the data and stimulating the brain in response, just to get FDA approval, for example, I mean, the bar is so high that it's one of the interesting things about the field, because it's what's happened in the field. And this again, I think, ties back to a very core computer architecture problem, is that because of power restrictions, and because, there's this sort of sense that we don't know what data is useless, so we don't want to discard or downsample or anything. the move in the field has been to build very, very domain specific devices that can only treat like one ailment. It can only be implanted at a specific depth in a specific brain region, and the FDA will approve and say, that, okay, this is safe. But so of course the problem there is, ultra specialization, has its problems. And so having a more general purpose platform to work with uh, would be nice, because you then get approval for one device that could work on a variety of different things. But I think the biggest stumbling block to the adoption of that one device has been questions like what you're asking, Tim. Like, is there a consensus on how aggressively can we downsample? What's actually useful data? How many channels, frankly, do we even need? I mean, we don't really even know how many sensors are needed for the different types of protocols that we want working on these chips. And all open questions.
Yeah. Well, as you were talking about that, something that's sort of a distinction between those two problems is that oftentimes it seems like you're looking for emergent phenomena in neuroscience, right? Where it's really it's not one piece of data that's hidden amongst all these others. It's actually the functioning of the system as a whole is what you seek to understand, which is a much harder problem to sample.
Yeah, and there's, I think, an interesting kind of thing to add on to that, which is that a lot of these implantable devices, what's increasingly being found is if you can detect that emergent phenomenon, and if you can be very targeted at stimulating the brain in response, if you know where you need to stimulate and with what frequency, what you can do actually is actually change the underlying plasticity of the neural circuits. And so what people, I mean, what's been observed with people with epilepsy, for example, people who've had implantable devices sort of put into them because they suffer from seizures. If you can find the right emergent phenomenon to target, if you can target it well, your implant needs to perform fewer and fewer stimulations through the course of its lifetime, because the neural circuits actually just get the plasticity, and it gets rewired in a manner that reduces the incidence of those seizures going forward. So there's this kind of feedback loop between building these systems well and the underlying brain substrate too.
So tell me something about this brain-computer interface. So is it something that what the neuroscientist already decoded, and based on that, we are trying to build some device for extracting information and also stimulating the brain, or it is also a way to just understand how the brain works, or maybe it is both, but maybe you're focused on one area more than the other?
Yeah, so it's all of the above. I mean, basically this field, I think, has been, I mean, it's been around for a while, but I would say the last 20 years maybe has seen active coalescing of this as like a specialty. And the longer term sort of vision is that you'll be able to build devices, not necessarily implantable. Some of them could be non-invasive, but either way, there'll be devices that can read neural activity and decode them. And that decoding can have a lot of benefits, everything from treatment of neurological disorders. So for example, the FDA today actually approves a list of some 30 to 40 ailments that you can get one of these implants for. It's everything from schizophrenia and epilepsy and Parkinson's disease, all the way to even things like, obsessive compulsive disorder, and even addictions and morbid obesity and other such. There's a lot of different conditions for which the FDA is looking into this. And that's kind of on the treatment side, but we know so little about the brain that basically these devices that have been deployed in patients are acting as a research platform for many neuroscientists. They read the data off them, they try and understand what that means about the cognitive decision making that the individuals are taking up. So it's really a bit of both. I mean, these devices are very much in their infancy. I mean, the kinds of things we can do today involve everything from stimulating the brain to mitigate symptoms of those disorders. You can also use them to manipulate prostheses. You can use them to manipulate, for example, wheelchairs. I mean, that's not an uncommon use. But longer term, there's there's people that have done some really interesting experiments, and that they've shown, for example, that it's possible to read brain data and try and reconstruct the image that a subject might be looking at, the subject from whom the brain data was extracted. Obviously, we don't get pixel by pixel resolution on these things, but what you can get is you can actually start getting coarse-grained approximations of what they're looking at. And so a lot of the focus has been so far on the algorithms and the decoding, making sense of the data you're pulling out. But the systems questions, have not really been looked at to that extent because it's been such a niche field for so long. Especially given our field's current focus on this, resolving this tension between general purpose and the domain specific, it seems like such a great target for us to have a say in that conversation. Because they're making very important decisions right now about how much data to downsample and what is actually useful data and what can be discarded based on what the community thinks are the best possible power efficient targets you can meet. We can have a say in building the systems and telling them how well you can actually do, and that can help influence the algorithms and act in, influencing, act as sort of that part of this bi-directional loop. I don't know if that answered your question. It was a bit of a rambling, brain.
No. So another question, a follow-up question would be, so currently who are designing these devices? Because it doesn't feel like we as a community are involved in that process. Yeah. Or is it something we should be involved? Not just the system, the whole thing.
I think we should absolutely be involved. And it's actually some of the players in this space are people we're quite familiar with. So, the most active, the most sort of the company, the startup that's been getting the most publicity is, of course, Elon Musk's Neuralink startup. So they've been in the press a lot. But Facebook, they have their own internal BCI team. Now, not all of them are working on implantable versions. Some of them are working on non-invasive versions of these things. But there's at least another dozen or so startups working on several flavors of these devices. Medtronic, as you might expect, they are in this space. There's other companies like Kernel, Longevity. There's Longevity is building these cranial prostheses that they can sort of literally act as like a skull replacement for some patients. And because they are not, they won't have to be embedded under the skull on the brain tissue, you can embed electronics on the actual cranial prosthetic, and technically it should be able to sustain a higher power budget. So there's a lot of work in this space actually, and yeah, it's ongoing. And I think, maybe just to throw this out there, I think we can get involved not just in architecting these systems. The where we can play a role is getting the mix of domain specificity and generalization correct to meet power targets. How to make them modular, because the FDA approves one of these devices after 8 years. And now if you suddenly decide that you want to implement support for another algorithm in it, going through another 8 years to get FDA approval is just a non-starter. You need to figure out how to make these architectures amenable to plug and play in a manner that fits these approvals. We can get involved in the languages and the software stack to actually program this stuff. And the other piece, security and privacy. Right now, there's implants, several of the state-of-the-art implants don't even support, basic encryption. So there's a really important role, I think, for people of our community to jump in there.
That's really cool. Yeah, I'm thinking about the that's a nice description of some of the opportunities there. And yeah, as a field, one of the challenges when you try to do cross-stack work like this, it's pretty cross-stack, right? Is the whole infrastructure piece of how do you do this work? Does this work require that we all are doing in vivo work, or are there opportunities here for people with some reasonable delta from their existing skill set to contribute in that space, in your opinion?
Yeah, and that's been the challenge, I think, for us, for my students and I getting in this space. We've published a few papers, but it's taken 2 years, 3 years of infrastructure building to get there. I mean, it's a significant time investment. I mean, at least what we have found is that the hard part is, obviously there's some amount of actual data that you need to collect in vivo from say animals or humans. I mean, having done a little bit of lab work, I can say that is, I am not particularly well suited for that task, and it requires a set of skills that really, I mean, people have to specialize in that for years. What we have found to work for us is, partnering up with neuroscientists in the field and getting data from them. The challenge, of course, there, which is an interesting one, maybe it's an opportunity too, is that, uh, computer architects, we can build things that create a new universe. And if you, so there's, run into this challenge where you ask people, if I were to build such a system for you, what could you do with it? And it sort of pushes them into thinking in ways that they're not necessarily accustomed to. So they may not have the answer for you. So there's this, again, this like bi-directional conversation that is maybe the hardest part about this research, where we don't know what is most useful to build. Is a chicken and egg problem. The algorithms and the workloads aren't there yet because the hardware wasn't around. So how do you converge on knowing what to build? If you can find, I think, at least for us, the way to have that dialogue, then you can step away, I think, a little bit from all the wet lab and in some of the infrastructure building, at least. But there's other infrastructure building that I think for people in our community is just going to be unavoidable. So I think, for example, in this space, when you're dealing with such low power designs, building chips, getting at least to place and route numbers, that kind of thing is really unavoidable. You sort of have to have that level of confidence in what you're designing. So I guess it really boils down to the graduate students, like anything else, and whether you find whether your graduate students have the the pain threshold to push themselves through that.
Well, I was struck by, I think as professors in particular, the question of, okay, can I do this? How much do I have to change what I'm doing to be able to work in this field is a question that shouldn't limit us, right? I mean, who else has the privilege, right, of being able to choose what they work on in a way that they think is going to influence the world for the better? I mean, why else do this crazy job?
I think we are that way as a community, Tim, if I could just jump in, just because of examples that folks like you have set, Luis, Ceze and Karen, all the DNA work that they've done. I mean, that kind of, headfirst jump into learning entirely new things, that I think acts as, that lowers the bar. I think it encourages the rest of us to give it a try and see what happens.
Well, I was going to say that, one of the things that that I see as a field that we're kind of going through a phase transition is computer architects. I think computer architecture for a long time has been a field for computer architects. It's about how, and we sort of were keepers of the problems and keepers of the solutions. But and so we kind of cycled, and we made a great progress living in that cycle, and we had great support above and below, the sort of system stack. But now we're kind of entering this phase where we have to be exporting our knowledge in a way and making it accessible to broader sets of people, because they need us now in a way that they never did before. So this is just a great example of that kind of exporting of knowledge. That how do you build a radically more efficient system, and how do you take these concepts and core ideas that that we know how to do and bring them to have this broader impact in the world. And at the same time, as you rightly mentioned, that is not a one-way arrow, right? And in doing so, we will also enrich what it means to do computer architecture and bring those things back to our community. And I think, honestly, that's one of the things that is a real strength in computer architecture as a field, is that we've always kind of been forced into this thinking of, we operate on a longer time scale than the rest of our computing colleagues, right? It's like, we're forced to make decisions that have impact 8 years later. That's kind of the time scale, the time constants involved in doing architecture are longer. And obviously people are trying to work to make that shorter all the time, but at the same time, like, you know, that longer term view of like, yeah, where should we be as a field in a decade? You know, I think these are exactly the types of, you know, your work I think is a great example of the types of, you know, bringing these things back into to computer architecture for us to really think about and saying like, yeah, what is it going to mean to be a computer in 10 years and 20 years and 40 years? It's not going to look like what it looks like now, that's for sure. So, and you know, who else is going to define what that looks like other than us?
Yeah, I think, yeah, I mean, the idea of just abstracting away the nature of what it means to compute and finding, I think, just principles that you can lift from nature. Not all principles that you lift from nature may necessarily be amenable to the substrate with which we build our digital ecosystem. But if you can find the right links, I think there's a lot of power to that. And I think I agree with you, Tim, that like our community, I think we think about those problems a lot. So in many ways, we're well equipped to go have those conversations with um, people in other fields, I think.
But I will also echo your sentiments that oftentimes that's a conversation that people have not ever really had when you talk to someone. It's like, if you have, you know, what would if this box did exactly what you needed, you know, what would that look like? And it's like, wow, never put myself in that sort of level of unconstrained thinking. But I think that's exactly the right conversation that's needed here, and in many other areas where we interface with sort of problems of human importance.
And I think that's another space where architects have some perspective that makes that task easier. I think, you know, from just maybe nuts and bolts, you know, publishing kind of perspective, I think we're used to encountering chicken and egg problem where, you know, we don't necessarily have the workloads to justify fully building something out, but we'll go ahead and build it and see if they will come. And I think that receptiveness helps in going and having conversations with people in other areas, because even if they can't envision the workloads that they would, you know, run on the systems you're building, you'll at least be able to, you know, your work will still have value. There'll be people who will be interested to read about it.
Yeah, I just want, yeah, I echo that completely, and I think that's, you know, I hope when people are thinking about that as what it means to be a computer architecture paper, when you talk about publication, I mean, it's always a question when you're doing something that's a little outside the box. You know, you want, you know, how far outside the box can you get? And so a top paper in computer architecture, but you know, I think that's just from a totally different area and sort of computer security work that we did. You know, the first paper we wrote in that area was really not a good design at all. Like, it was a really cool idea, but the community, I think, you know, was I really appreciate the ability to be able to write those early papers and to have conversations, and for that to drive that work forward, and for it to be given, the community to give it the time to sort of unfold, and say, yeah, you know, this is a good direction. Let's keep doing this, because doing that kind of bold work is really hard. And, you know, if your students like can't publish for 5 years because they're, you know, they're building this all out, it's never going to work. They need to be able to have the opportunity to engage with the community and to, you know, they need that feedback, not just that positive feedback from not just their advisor, but the community also. So I hope that computer architecture, we can, you know, keep some of that character as we kind of go forward in the field. I'm optimistic that we will.
So students get pretty motivated when they can envision what their work could enable. And I think that's the exercise that Abhishek mentioned, that just going through that process of imagining what we could do if we have these maybe infinite channel, and we could probe all the components in the brain, and we could get a very high sampling rate. So even for me, actually, like, I don't know what that would enable. Like, what do you think in 30 years or 50 years, maybe we will not have a very large bandwidth, but most probably a power efficient, high bandwidth interface would be possible. So in that case, how do you think the future will look like?
Yeah, so that's a good question. I mean, I think we're already getting to a point where these devices are being safely deployed in chronic ways in patients who need them. Now, the patients who go ahead and consent to have these devices, inserted, they're really, I mean, they have very aggressive forms of what they suffer from. Very, very, it's there's a lot of suffering that they are undergoing to sort of want to take up that risk in a way. What I would be interested to see is, I've worked a lot on the implantable side, but I'd be very curious to see how the non-invasive and brain interface technologies pick up, because if there are ways to pick up signals from the brain with sufficient spatial and temporal resolution to do useful things without having to actually surgically insert them, that would be, I think, a big next step. Ultimately, the more we learn about I think there's two things. We learn more about the brain, the more data we can extract from it. And the more we learn about the brain, the more useful systems that we can build. I mean, if you think about it at a very core level, we have such a noisy communication channel with one another and with our digital ecosystem. It's through typing, it's through speech, and it's through vision. But they don't get to the core of what cognition means, and unlocking that and having a better access to that from the digital world. There's sort of really limitless in terms of, I think, what you could do. I think, though, that again, it's important really to stress that with all of this opportunity is going to come a lot of, I mean, we have to worry a lot about privacy of data, security. There's going to be serious ethical considerations that come into play. I mean, if you can start detecting what images a user is looking at using MRI, maybe not even like an invasive technology, that's where policymaking will have to come in. And actually, there again, I think computer architects can play a major role, because we've sort of had to tackle some of these issues with the systems that we have built. If you look at the IoT space, spectrum allocation questions are something that our community has had to get involved in. Security, privacy, these are things we think about. So beyond, I think, just the opportunities that such technologies may enable, I think we can play a real role in shaping up the right ways to harness these technologies for, well, to put it in a naive way, I suppose, for good rather than for bad, although it's never really that cut and dry, these things. Yeah.
Tim, do you want to add something about the future, like maybe what it would be in 20 years and 30 years?
Oh my gosh. I don't have a particularly great track record as a futurist, I will say.
I skipped the question. I evaded that answer.
I give a talk to undergraduates about sort of what computing might look like, and I don't pretend to say that I know what it's going to look like, but I think it's useful to remember what we're training people to, the field that they're going to work in. The undergraduates and graduates are entering a field at the beginning of their careers, and the field they exit is going to look nothing like the field they enter, right? Because if you look, and the data for that is very simple. Look, one generation ago, what a computer looked like. One span from the start of a career to the end of a career ago is basically like the Apple II or the Apple I, like my slides I have a little picture of it with Woz's signature at the top. So like from there to now, that's one generation's worth of change in computing. So I see no reason to expect that the change from now to the end of a new career starting today should be. I don't see any reason why it wouldn't be as radical a change. So I have no idea what that is going to look like. And anything I say, I think, will be comically bad in retrospect 20 years from now. But I will just say again and again, I'm always shocked by it. I think those changes. And you know, I'll tell you one little story that that really sticks in my mind. And this isn't even that long ago, but sort of when I was a graduate student, you know, there was this like future vision of computing video that was produced, and it was, you know, it was like all these different kind of you know, what might a computer look like, and many of them kind of looked outdated even by the time that I saw it. But one, you know, was like a translator device where someone was trying to talk to someone, and they held out this device, and this person you know, said something, and then it just translated it back naturally into this other language. And in the room, everybody laughed because the idea of that was so ridiculous that such a device could exist. Okay, it was so far beyond their ability to comprehend that such a device could even exist at the time that it was comical. And like, and now obviously that's, I mean,
we have it in our phone.
Right? Like,
yeah.
Yeah, exactly. So it's like comically mundane now, right? And so the the gap between the comically far-fetched and the comically mundane is like 20 years, right? So, you know, so what's the future going to look like 40 years from now? Like, I dare not imagine. But, you know, but you don't have to know what it's going to look like. I do think that you can just follow the gradient, right? And I think, you know, so what is the direction in which things are going? And I think the direction is very much along these lines that we've been talking about today. And I think the direction is also very much, you know, along how do we build more trustworthy computing? How do, you know, things that I really, my life will depend on every day. I fully expect that to be a normal thing. You know, how do I build more secure? How do I build more efficient? How do I build more connected? I mean, these are all things that we need more of. And I think as academics, we also have a unique opportunity, which comes with responsibility also to kind of look at these questions, not just from a market standpoint, but also from a sort of a potential for human good standpoint. So that's why I think all the stuff that being discussed today is so interesting and exciting to me, and it's a great thing to be a part of. How's that?
Yeah, I'm really excited about the future. Yes, we don't know what it would be, but it would be something really exciting that we can imagine. Abhishek, any concluding remarks for students who may be thinking about pursuing this type of research?
Maybe just, if there aren't all that many papers written on it, that's a good thing. Don't be alarmed that there isn't that much prior work out there. That can be a sign that it's a very fertile field to get into. The reason I say that is I made this, I think when I was getting into graduate school, the way I was thinking about things was, the courses I most enjoyed in my undergrad, those are probably the areas I should go do research in. And that may be true, but there's also the case to be made that maybe you enjoyed those courses most because they were the most mature. There's the best textbooks written on that stuff. There's the most resources available. And so maybe those are not the most fertile areas the low-hanging fruit may be gone for now. I mean, I think these things operate in cycles, and low-hanging fruit always come up when technology constraints change. But anyway, so what I would say is, I think this intersection between the brain sciences and systems is very interesting. And I would say that there are challenges in overcoming some of the lack of maybe introductory material, the lack of infrastructure and such. But I think there's a lot of interesting questions that can be answered even with very primitive models and back of the envelope calculations, and there's a path to doing good research there.
Yeah, you're here. I think yeah, and I think that things remain curious. I think that you know, as you rightly pointed out, Samara, at the beginning, you know, there's these things that come along and they're unexpected. And, you know, I think that as computer architects, we're good at thinking about understanding trade-offs, and there's a fundamental trade-off here between, you know, your you know, remaining open and curious and interested in all kinds of different things, but also making progress and getting work done, right? And these two things are always in tension, and a healthy balance between the two is good, because it's easy to kind of get so focused down into, okay, I'm pushing this line, you know, I'm pushing this line forward each step of the way, and not being open to other ideas on one extreme, and the other extreme of just sort of dancing around between the next thing that interests you. It's like doing progress is always painful, and but it's that good kind of pain that, you know, like exercising. You know, it's like it's good for your brain, good for the field, and those two things I think are you know, to be kept in balance.
That's a great advice, and yeah, I think it was a very interesting discussion. I'm really fortunate to have you two to have this discussion. I learned a lot, and I'm pretty sure other people will learn a lot. And thank you so much.
Can I just say that I think our field is very fortunate for you to have you, and to for you to bring, I think, this, you know, these discussions, community. I think it really means a lot to a lot of people, and I think it's a wonderful thing. Thank you for doing this.
Thank you. I really enjoy talking to people.
Thanks to both of you. This was a lot of fun.
Absolutely.
Okay, that concludes our session.